Hey everyone, and welcome to another episode of Practical Parallelism in C++. My name is Nick, and today we're going to introduce a new type of parallel programming, or a new model for parallel programming that's pretty significantly different from the ones we've looked at previously, which is message passing using MPI. So all the different kind of threading models that we've seen previously are based upon shared memory. So we have to distinguish between what shared memory means and what message passing means. So when we're talking about shared memory, like we used in pthreads, for example, what we could do is, say, take the case of Gaussian elimination, where we passed every single thread a pointer to a matrix that we allocated and initialized within a main function. All we needed to do in order to pass that data to the threads was just pass a pointer to the data. And this is because of something very fundamental with shared memory, in that everyone is within the same address space. So while they may have a separate stack for every single thread, so we can have all these local variables that are the same name. So we can have, every single thread can have, say, their own unique TID. So they can say int TID. That pointer that they have to that heap allocated memory, which is that matrix, that is going to be the same for every single thread, and they're all accessing the same piece of memory. Now, message passing is fundamentally different. So message passing, it's different in the fact that you don't have multiple threads within a single process. Message passing, you have separate processes altogether, which means that every single process will have its own stack and its own heap. So if we want to communicate, we can't do it through just pointers anymore, because pointers with the same address in different address spaces will point to different memory. So we've got to be a little more careful there, or rather, what we typically do is in message passing, it's more point-to-point communication. So we send specifically to one process, and we receive specifically from another process. So it's typically more point-to-point communication based, which is why it's called message passing. So you pass messages to other processes, and so it's kind of like, you can think of it like a letter, right? So you send a letter, across the way to somebody else, and then they send a letter back to you. So let's kind of jump into an example and see how we implement, a basic kind of hello world program using message passing. So let's open up MPI hello.cpp. So we'll of course have to include a header. So that's what this MPI H is. This gives us kind of our interface for using MPI. Then in here, we can go ahead and jump down. Here we just initialize, or we just set up a couple variables that we'll use down here. But they really only make sense in the context of the MPI functions. So the first thing we need to do is we need to initialize an MPI execution environment. So this just says, this is kind of where, the parallelism starts here, that, for MPI. So we do an MPI init, and we'll just pass it argc and argv, which is typical. So we just take whatever main has for argc and argv, and then we'll just pass it on so that every single process will also get this argc and argv. Then we'll look at a couple special functions that we have as far as MPI goes. So the first one is MPI com rank. So what MPI com rank does, it says, which process am I? And in order to better understand what we mean by that, we should really understand of this MPI com world right here. So the way that MPI works is that you'll have something called a communicator. And a communicator is basically a grouping of all the different processes that you're running. So within a grouping, within a communicator, every single process is called a rank. So a rank is just another word for a process. And so this MPI com world right here is just kind of the default communicator. So you can have a custom communicator, but in this case, we're doing something very simple. We're just printing stuff out. We'll just use the default. So again, MPI com rank gets a specific process's rank. And then that's just which process it is inside of a communicator. And so that's going to be a static value. So every process within a communicator will have its own unique rank. So then we'll have the ability to get the size, right? So all size does is it will get the number of ranks within a specific communicator. So we'll get MPI com world, so all the ranks within this communicator. we'll go into size. And so that's what we have up here, right? So we have an integer rank and an integer size. So we pass in the address of that integer rank here, and it'll get filled with the specific rank of that process. And then over here, the size will get filled with the total number of ranks within the communicator. And then we can even get the processor name. So MPI is typically used on kind of large-scale clusters. So sometimes it's important to know, what exactly physical machine that we're on. So the actual implementation of this MPI get processor name, it's implementation specific. And so a lot of times it'll be something like the result of get host name, uname, or sysinfo. So it'll just be kind of the return of one of those kind of three things generally. And so what we do is we're just going to pass it this buffer right here, so just an array of characters, and then it'll just fill within that array of characters whatever the name is, which is usually the result of one of like these three things. And then we'll also give it the address of another integer, which will just say how many characters it wrote as the name. So then down here we can go ahead and print out all the things that we collected. So we'll say hello MPI, we'll print out what rank we are, we'll print out the number of ranks within the communicator and the size before finally calling finalize, right? And then we can also call return 0 right at the very end. So we call, our MPI stuff is really bounded between the MPI init and the MPI finalize. So let's see how this works. So we'll use a special compiler for this. So it'll be MPI C++, and then just like all our other compilation with G++, it'll be MPI C++ -o, MPI hello, hello, and then MPI hello.cpp. Okay, so let's go ahead and run it, and we see that, it indeed does run. So it runs with, this specific process has rank 0 and a total size of 1 because there's only a single process running. And then it says the processor name is CBA, which just happens to be my username on this account. Now you may be wondering, well, this seems fine. I understand this, but where's the parallelism? I only see one process. Well, it turns out we have to use kind of another interface in order to launch multiple processes. And so we'll use MPI run, and then we can use -np to set the number of processes we're going to spawn. So every process will run this application, but it will have a unique rank. And so MPI run kind of just spreads out these processes to whatever it can find. And by whatever I can find, what I mean is there's a specification for the number of devices that I can schedule things to, or I can send these processes to. Now there's a default one that typically is created when you install MPI. And so what that will do, it will just be, say, in my case, it'll just be on my local desktop. But if I say I had a cluster somewhere that I could schedule things to, I could set that up as well in another file. But in this case, we'll keep it simple. We'll just use the default, so I don't need to specify a special file that, lists where I can send tasks to. So in this case, I'll launch 4 processes, which will just get scheduled on my local CPU. And then I'll run the application MPI hello, right? And so here we go. So we've got now all the size of, so when I got the size for all of these, it's now 4 because I spawned 4 processes within that communicator. And then each one has its own rank. So here's the one that's rank 2, rank 0, rank 1, rank 3. So again, there's no real kind of ordering here. It kind of just happens whenever a processor or whenever a process decides to print, goes ahead and prints out. So let's run it a couple more times. And you see we get a similar problem that we had with, say, pthreads and the standard threads, where it's not thread safe. So cout isn't thread safe. So even though it's, different processes and different threads is what, instead of just being the same process in different threads, there's still the synchronization problem. And we'll talk about how we do things like synchronization because we're talking about different processes now and how we can use MPI to fix this. And yeah, so sometimes, it seems like it gets ordered exactly as we'd expect, 0, 1, 2, 3. But again, and in other cases, it'll go out of order, or it'll get intermingled or interleaved on the same line. So that's going to go ahead and do it for this video. So that's kind of our introduction to MPI. We'll talk about the synchronization in the next video. As always, you're more than welcome to come visit me at github.com/coffeebeforearch, where we've got all the code for these videos. So we've got C++ stuff, Python stuff, parallelism stuff in GPUs as well as in CPUs. So we looked at practical parallelism in C++, and we looked at MPI today. So here's that MPI hello.cpp. Feel free to download this, check it out. All the code is always going to be available, and feel free to comment if you have any questions, or contact me if there's something you'd like clarified. But as always, I'm Nick from Coffee Before Arch, and I hope you have a nice day.